Good evening from sunny Tokyo. My name is Simon Downs, and today it is our pleasure to introduce Dr. Mary Zenobi-Wong, who will be talking about the bioprinting of cartilage and the goal of translating her technology to clinics to improve the outcome of current cell-based therapies. Now I will pass the mic to you, Dr. Zenobi-Wong. Thank you.
Okay, so welcome everybody. As Simon said, I am Marcy Zenobi-Wong, and I'm a professor on the topic of cartilage engineering and regeneration. My research group is in Zurich, Switzerland, and I will be talking to you about some of the challenges of bioprinting cartilage and what excites us about this field. I know we have a very broad audience today, so I would like to first introduce you to what cartilage tissue is, and there are certain properties of cartilage which I think will make it particularly a good target for the technology of bioprinting. I'll talk to you about what exactly bioprinting is and how it is different from the other 3D printing technologies that you've heard about this week. There are specific requirements when you bioprint as opposed to 3D print. And it's particularly what we call the Bioink. This is the components that are in the cartridge of our bioprinter, which makes the field so challenging. And I'll talk to you about what are the qualities of a good Bioink and how you can develop one. And finally, some limitations or the challenges, I think, that will have to be overcome for this kind of technology to enter clinics. Okay, but first I'd like to convey that I think bioprinting is the future of personalized regenerative medicine, and our view of how this works is shown in this schematic here, where you can envision that there's a patient that has just gone skiing and has had a collision with another skier, has come down the slopes with a lesion in his knee. Right now, there are not so effective therapies for healing that lesion. And what we're envisioning is that one could make a personalized graft to heal this injury. And it's personalized because it could have cells from the patient, and it would also be designed for the actual shape of the hole in that person's knee. So you would imagine the person would get some kind of MRI scan so that we know what shape the geometry of this defect has, and there would be a computer model made of this missing piece of tissue, and this file, it's called an STL file, would be sent to the bioprinter, and using cartridges of this Bioink, so you can see schematically the black and the yellow and the red tubes filled with cells, this Bioink could be extruded in a way that matches the native tissue. So for instance, native tissue has different layers. This is schematically illustrated on the bottom. We call it the superficial layer, the middle layer, and the deep layer, and then there's a layer of bone underneath. And you could really take your cartridges with different components and then print a graft that would fit exactly into this patient's knee. This is a picture of the bioprinter, and it has a top and a bottom. On the upper left is a picture of the top of the bioprinter, and you can see that there's room for different cartridges. So you can see this little orange structure here. This is one of the cartridges that has been mounted in the bioprinter. But there's also room for up to 8 different cartridges. So in principle, one could print a piece of tissue that has different amounts of cells, different kinds of cells, that is mixed with different kinds of polymers to make a very complex, architecturally complex structure. So what happens in the bioprinter is that you have your cells in some polymers in this cartridge, and the cartridge is put under pressure, and this pressure essentially just squeezes out the Bioink onto a collector plate, which you can see on the bottom right image. So this metal round disc is called the collector plate, and on top you can see the needle and the nozzle through which the Bioink is extruded. And what happens is that the collector plate is just moving in X, Y, and Z space, and the nozzle in our printer is actually held stationary. And this allows us to print quite quickly. So this is something that we want to do fast because our ink contains living cells. And this is what you would use, the technology. So this is basically how bioprinting works, and the difference between bioprinting is that all of the conditions that we use and the materials that we use have to be compatible with cells. So we could never melt PLA at 200 degrees Celsius because, of course, your cells would evaporate. Everything has to be done under quite low pressure and in an aqueous solution. So getting back now to the kind of tissue that we are trying to print in the lab, this is a tissue called cartilage, and there are several sites in the body where you find cartilage. The most obvious and common one is that it lines the surface of all joints. You can see the end of the knee joint in the upper left, and it's a shiny, smooth surface which helps your joints articulate. You also have cartilage in the nose to keep the nose structure erect. You have cartilage in the ear, and it's the shape of the ear which is actually directing the sound waves towards your ear canal. So cartilage is in all these cases a functional and a structural tissue. If you look at a higher level of magnification at cartilage, these are the histology slides. You can see where these white dots are the cells of cartilage tissue, and you can see that they're surrounded by what we call an extracellular matrix, and this contains a lot of molecules and proteins which are important in supporting these cells. And then if you look on the far right, this is the molecular structure of cartilage. So it has these long collagen fibrils and a molecule called aggrecan, and this is the molecular environment in which a cartilage cell would reside. The important thing about cartilage, there's several important things. One is that the tissue, you can see it looks very white. It doesn't have any blood supply. And that means that the oxygen saturation of this tissue is quite low, and that the cells can exist in a low oxygen environment. And this is important when you go to print a construct, that you don't immediately have to attach your cartilage printed construct to a blood supply, which you have to do for a lot of other tissues that have a higher metabolic demand, because cartilage is kind of an easy tissue. The cells will be fine for several days without being close to a blood supply. And this enables the translation of this kind of tissue and the fabrication of this kind of tissue to proceed, I think, in a more easy way. Okay, so that was cartilage, and as everyone knows who has sports injuries, these kind of cartilage tissues can all be damaged. You could have some kind of trauma, and there's a quite good need to come up with replacement tissues to treat these kinds of injuries and diseases. And this is where bioprinting comes in, because bioprinting, as everyone knows, is very good at reproducing structural properties, mechanical properties. It's very good at creating intricate shapes, and this is essentially the role that cartilage plays in the body. It's structural, it's functional, and that's why there's a happy marriage, I think, between the bioprinting technique and cartilage. And just to illustrate that, there is pictures here. This is a histology section of cartilage where these little brown dots are the cartilage cells, and this pink stuff is the extracellular matrix. So this is what native tissue looks like. And if you look on the right-hand side, there's a picture of cartilage cells, these brown dots, which have been incorporated into Bioink and have been extruded and printed. And you can see that even at this very fine level of resolution, the bioprinted tissue looks quite similar to the native tissue. Okay, so I showed you the bioprinter, and I said there was some cartridge, which is filled with cells, it's filled with signals, so things like growth factors, which are important to keep the cells functional, and it's also filled with polymers, which are dissolved in an aqueous solution. So you mix all these things together, and this is your Bioink. And the challenge for bioprinting is often to come up with the design of this Bioink, particularly what polymers you use, because a Bioink and the printed construct has to fulfill several requirements at the same time. And this is illustrated here where you print something like cartilage or like bone, and it should have mechanical properties to support the body, to support the body's movements. The actual Bioink, when you extrude it out of this cartridge, it has to have certain properties. So it can't be too watery, because after you extrude it, it will start flowing. Can't be too viscous, because then you'll need too high a pressure to get it out of the cartridge, and you might kill your cells. And also, perhaps the most challenging is that this Bioink, this combination of ingredients, has to be biocompatible. That means that it has to contain polymers that the body is not going to reject after you implant them, and they have to not only be biocompatible, but also to support the cells so that the cells can continue to grow and can continue to secrete those matrix proteins that I showed in the previous slides. So I'm going to talk a little bit about what printing properties a Bioink should have first. The most important printing property of a Bioink is that it undergoes a process called shear thinning. And this means that as you extrude or try to push the Bioink through a narrow opening of your needle, that as the shear rate goes up, the viscosity of the polymer will go down, so it will be able to flow. Analogous to how when you push on a tube of toothpaste, the toothpaste flows out of the tube. This is one of the first properties a Bioink should have. And I'd like to show you, once you have the shear thinning Bioink, how you have to optimize the parameters of the printer itself. So it's not a plug-and-play operation like it is with a lot of these desktop 3D printers that you can buy. There's a lot of optimization, and I just show you some of the parameters that have to be optimized. The pressure that you put on the cartridge, how fast your nozzle is moving, the temperature of the printing, because a lot of these polymers are what's called thermal responsive, so they behave differently and have different viscosities at different temperature. The layer thickness, this is something that everybody knows who does 3D printing, and also the geometry and the diameter of the needle has to be optimized, because if it's not optimal, you could create within the needle a lot of shear stresses, which might be perfect for printing, but also kill your cells because the shear stress is too high. So in this image is just some pictures of how much patience you have to optimize the printer. This was where a graduate student in the lab was extruding with different line spacings, and you can see that if you use 0.18 millimeters as a line spacing, you have a very bad print. And it gets a little better the smaller the line spacing is. But you also have the possibility to optimize the printing speed, as I told you. So this is here printing that has gone very fast, so 250 millimeters per minute. It's still a very ugly print, but it's something that you can really improve if you start to print slower. Okay, let's imagine now that you have your Bioink and it's been nicely extruded. There's another process that has to happen, and that is that the extruded polymer has to be cross-linked, because before it's cross-linked, it's still a paste. And there are many different Bioinks that are being developed. There are a few that are commercially available, and for all of these, you will have to trigger the cross-linking after you've printed your structure. In the example here, we use a polymer that can be cross-linked by exposure to UV light. And so this is an example of a T and an H that has been bioprinted. And you can see that after cross-linking, you can take forceps and actually stretch it and deform it. Before cross-linking, it was a paste. So this is another critical aspect, is that the polymers need to be cross-linked by UV light in this case, or sometimes by temperature, by a change in pH, by the addition of cations to convert it from your printed paste structure to something that you can pick up and eventually implant. Okay, the final thing that I'd like to say about how to print structures that are geometrically complex is the need often for support structures. So if you were to try to print something like this is just with a standard 3D printer, you know this overhanging structure here has to be supported, otherwise it will sag when it's printed. And there's always an optimal way to do a print. For instance, if you're going to try to print something that looks like a table, you would probably not try to print the overhanging part of the table, but flip the table upside down, print the base of the table, and then the four legs, so that it's all self-supporting. The same is true if you try to print structures out of cartilage. So this is an example where we tried to print using our cartilage Bioink, which is this white stuff here. We tried to print the letters ETH, and there are certain parts of the T which are self-supporting, and this part here is easy to print, but the overhanging stuff is quite difficult to print because the Bioink will sag. And so what's often used is to combine your Bioink of interest with a co-extrusion of another polymer, and this is represented here by this clear picture. This is something that you can just wash out afterwards. Okay, so let's go on. And then I'd like to show you some examples of actual bioprinted structures. These are our cartilage Bioink, which has been combined with cells and are growing in culture media. This is this pink solution here in these wells, and the cells are quite happy, and they can survive, and they can start depositing matrix proteins, so that with time a structure like this looks more and more like a cartilage one. But the field, I have to say, is really still at its infancy, where people are trying to optimize conditions so that you have properties that are not so far away from knee and hip cartilage, but that you can also support the cells. So often if you make a Bioink so stiff and so strong that it's no longer viable for the cells. And this is one of the big challenges of the field. Okay, and this is just an example of using the previous ink. You can make something that is quite deformable, so and quite elastic. Okay, so the second thing is to address the biocompatibility of the ink. I see already there's a question about stem cells. So the Bioink can also be tuned to support stem cells. So the cells can be just as happy in a Bioink as the cartilage cells themselves. What's trickier about stem cells is because they're not fully differentiated, so they can go off to become bone or fat or cartilage. It's often something that is a bit trickier to work with because you have to control this differentiation process. And when stem cells have been implanted in a cartilage environment, there's been occasions where the cartilage has turned to bone, which is something that's not desirable. Okay, so how could one make the cells truly happy in a Bioink? The Bioinks that are on the market right now and that are being developed have not so much what I would call bioactivity. So they're often a single polymer or maybe a mix of a few polymers. For instance, there's ones based on gelatin, based on hyaluronic acid. But if you look at the native cartilage extracellular matrix, so this is a picture of histology, and all the stuff in between the cells, I said, is this matrix. It's really full of lots and lots of proteins, lots and lots of matrix-associated proteins, a lot of growth factors, sort of an innumerable amount of signals which are important to keep the cells alive. And so this is, again, one of the challenges. If a cell is going to be truly happy in this artificial Bioink, it's advantageous to try to introduce a little bit of the complexity of the native matrix. And I would like to show you one idea about how one could achieve that. And this is something that we do in our lab, but has been also tried by many labs in the world, is that this matrix that I talked about can be ground up to made into small particles. You can also take the cells out. And this has been such a successful approach that you can buy as FDA clinically approved products these particles for cartilage. This is what we use, but also for skin and for parts of the intestine, for bone, for placenta. And because they're already particles, they can pass through the needle of the bioprinter. And just by mixing these particles into your more generic Bioink, you can tune an ink to have specific properties, more like a cartilage Bioink or more like a bone Bioink. And this is something that we've done successfully, because what we've seen is that if you mix in these extracellular matrix particles, your cells start dividing more rapidly. And that's because of all of these morphogens that are contained in these particles. So I like to think of the next generation of Bioinks as wanting to improve or enhance the bioactivity because these growth factors will be part of the Bioink, and the cells will feel more like they're in their native matrix. And I've just listed here for cartilage some of the key factors that are going to be important, I think, to add. These include fibroblast growth factors, transforming growth factors, insulin-like growth factors, and there's many ways that one can introduce these factors by these particles or actually by the growth factors themselves. And the field has developed a lot of methods to control the release of these bioactive factors over time, mimicking more and more how the natural matrix does it. Okay. So I would just leave you with a teaser about one of the applications that a lot of people in bioprinting are interested in, and this is about printing ears for reconstructive surgery, and this has been such a attractive target because there's such a complex shape of the outer ear. It's something that is very personalized, so it's as individual as your fingerprint, and again, this kind of structure is perfectly suited to what bioprinting is good at. So in the future, what we would hope is that you could use these scanners that are being developed currently. This geometry could be with an algorithm optimized, so you know exactly the shape of the cartilage that you want to make this patient-specific graft. This would then be converted into code that the printer would read. So in this case, these red lines correspond to how the ink would be deposited. The pink lines could be corresponding to how the support material would be deposited, and until at the end you would have a graft that could be implanted. Yeah, so I would like to conclude this talk with my view that there's a very strong and bright future for bioprinting, and I think the real areas which are going to be benefiting the most from bioprinting are the ones where the geometry of the graft is essentially its function, and this is true for many of the sites in the craniofacial area. It would be the case for like a breast implant, and down the road, I hope that these bioinks will be significantly strong to address the real weight-bearing applications like knee and cartilage. This is, I think, not there yet. So the inks still are quite soft, and this is because they have to support the growth of the cells. I think cartilage is going to be one of the easier targets of bioprinting, specifically because of this absence of vasculature. And I think there's a lot of exciting work about how one can enhance the bioactivity, and this is going to be important. And then finally, the challenges is to really understand the long-term fate of a bioprinted construct. This is a new technology, and there's a lot of potential defects in a bioprinted construct that don't exist with traditional manufacturing methods like casting, because you have to worry about the line-line adhesion, the layer-layer adhesion. So it's a really exciting new technology, and I think the field is going to need new standards and new norms to try to identify when these grafts are consistently and reliably and safely made. And the hope is that we will have a technology where we can print something that will eventually be replaced by a real living autologous tissue. So that was what I would have like to share with you today. I see there's a question about how do you estimate hip and knee cartilage being resurfaced so that the total joint arthroplasty is replaced by cartilage resurfacing? Here, I think, as I mentioned, the big challenge is the mechanical stability of the things that are being printed. There is a way that people are getting around that right now and trying to print something that has, from day one, the mechanical stability that is needed. And this is to use more traditional extrusion of thermoplastics. So polycaprolactone is a common one that's being used to print kind of the scaffold of this this surface. And then to get the cells in, this is done by kind of afterwards seeding this scaffold with some kind of cell polymer mixture that in and of itself could not support the load. But I think this is going to be, I think we're fairly far off from doing that successfully. And it could be the first clinical products that are translated are going to be ones where the weight bearing is not as high. Okay, and I think I also have measured that stem cell technology. I think in cartilage, the real challenge that one has to overcome is to maintain the stability of these cells so that they really remain as cartilage.
Okay, thank you very much, Dr. Zenobi-Wong, for a very detailed presentation. I can tell you from a layperson's point of view, this 3D printing of cartilage was, printing of cartilage was fantastically so interesting. I wonder if I can ask a question of my own. I learned so much in this presentation. One thing that interested me was regarding the shear stress on the cells and the needle. I imagine that you need very special needles for this printing.
Yes, so what we and others I think have found out is that you want to try to avoid a lot of regions in the needle where you go from something very big in diameter to something small in diameter. So you want to try to keep kind of a laminar flow. And the shape of the needle, it turns out, is that something that is conical, which is tapering, seems to reduce shear stresses the most. And I think the initial results are that in these conical needles you have the best viability of the cells. But it's an important factor. Even with a conical needle, if you're trying to extrude through something very, very narrow, I think your shear stresses go up, and you will damage your cells or maybe even kill them if the shear stress is really high.
So delicate. Thank you. And one other question was regarding perhaps the early trials when you were injecting. Was there a big problem with rejection or infection in the early stages?
So in my lab, we haven't. We have only started in vivo experiments, and it seems like there's no rejection. It's very highly dependent on what particular polymers one chooses. But I think there's enough experience with other more traditional applications of these materials to know which ones are going to be okay and which ones are going to be rejected by the body. And so when people develop a Bioink, the first thing they do is to look at ones where there's a history of safety. I
see. Well, thank you very much. I learned a great deal from this presentation, and I'm sure the listeners did too. And this presentation will be available on demand for listeners who would like to check in after. But we thank you very much and hope to welcome you back in the future for our presentations.
Okay, thank you.
Thank you so much.